Everybody, and we're back and we are going to do our problem set 6 solutions. So let's go ahead and let's take a peek. So looking at a snapshot of 2D particle growth. So we need to answer the question, which grains will shrink of these numbers, which grains will grow, how will the growth rate scale with time, sketch a plot of the average grain size, R bar versus T to the 1/2, what is the slope, okay. So we know for 2D grain growth, our rules are the von Neumann n equals 6. So n equals 6, dr dt is basically equal to 0. If it's greater than 6, it's positive, meaning it'll grow. If it's less than 6, it's going to shrink. So let's do 1, 2, 3, 4, 5, 6, 7. So 1 is 1, 2, 3, 1, 2, 3, 4, 5, 6. Make sure I count that right. 1, 2, 3, 4, 5, 6. So 6 sides. So this is going to be basically 0. Neither grow nor shrink. Let's do 3. So 1, 2, 3, 4, 5, 6. So 3 is also there. What about 2? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 2 is also 0. Let's do 4. 1, 2, 3, 4, 5, 6, 7. One's kind of 1, 2, 3, 4, 5, 6, 7. So 4 is going to grow greater than 0. 5, 1, 2, 3, 4, 5, 6, 7. Greater than 0, grow. So grow, grow. Let's do 6, 1, 2, 3, 4, 5. So this is less than 0, it's going to shrink. And then 7 is 4, so that's going to be less than 0, shrink. So how will the growth rate scale with time? So we know that our R bar squared minus R naught squared is going to be proportional to basically M times T, where M has these, again, that's in the notes, but it has this basically a exponential term with respect to everything else is just constants, minus delta G over KT over temperature. So I have this exponential and this 1 over T term. So that's M. So M. So how will the growth rate? Well, if you take the derivative, then you'll see it's going to scale with this, basically just with M. So this is going to be our slope. So if I plot this, R bar versus T to the 1/2, so R bar, and I do T to the 1/2, so I just take square root. So my slope will be linear. The slope value will basically be square root of M. But again, it's this term that the exponential relationship, the Arrhenius relationship with temperature will always beat it out. So the slope, as my slope increases, my temperature is increasing at reasonable temperatures. Excellent. Write out the chemical potential. So let me actually erase a little bit here. So write out the chemical potential of basically grain 1, grain 7, interface marked blue, which grain will shrink and grow, label the wells in figure 2, which was, okay, so I know if I'm over here, so if I can kind of zoom in and draw on this, so this is basically 1, this is 7, so my chemical potential of 7 is chemical potential of an infinite plate, yeah, U naught P, plus 2 gamma V bar over R. Chemical potential of 1, on the other hand, is going to be infinite plate minus 2 gamma V bar over R. So my chemical potential of 7 is greater than my chemical potential of 1. So, and I know I moved from high chemical potential to low chemical potential, so my atoms are going to move from 7 all the way to 1. So what's going to happen in that interface? It's going to move closer here. So 1 is going to grow, 7 is going to shrink. Makes sense with our kind of other rule previously. So where are the atoms going to move from? So they're going to move from 7 to 1. They want to jump over this little hill, not this big hill. Excellent. So my undergraduates actually measured the free energy for nucleation as a function of particle radius below. On the purple curve, indicate the critical radius and state its value quantitatively. Also indicate on the curve which radii will grow and shrink. So this is my R star at the peak of this curve. If I'm bigger, my change in free energy, so if I'm to the right, I grow. Over here, I'm going to shrink. And remember, this delta G for nucleation is equal to minus 4/3 pi r cubed times delta GV, where our delta GV terms is equal to delta HF delta T over Tm, I believe. And then we have a plus 4 pi r squared, and then our kind of basically our gamma, our area term. So I'm going to go plug that in into my Mathematica notebook. So GR equals delta GV times minus 4/3 times pi times r cubed, and plus 4 times pi times r squared times gamma. Not gams. Gamma. So if I take the derivative of g of r, set it equal to 0, solve for r, I will find, and then, well, that's derivative. Oops, excuse me. I need to solve derivative of gr with respect to r, set this equal to 0, solve for r. So this is my r crit. So I'm going to say this. That basically r crit equals this, slash dot delta gv goes to delta hf times delta t, our amount of undercooling, divided by tm. And there we go. We have our nice, beautiful relationship right there. So my r star is equal to, again, we'll pull that up here. This value, whoops, just like 2 gamma tm equals 2 gamma tm divided by delta hf, and then delta t. That delta t is a critical relationship, one that we've kind of talked over a bit before in class. So we've got that. We answered the question. We state the value quantitatively, which values we're going to show. Okay. What will happen if the undercooling is increased or not? So again, delta T is my amount of undercooling. So delta T is equal to Tm minus T. So if my undercooling is large, my temperature is cool. If my undercooling is small, my undercooling is high. So if I increase my amount of undercooling, my temperature becomes larger. My curve will shift to the left. Smaller radii. If my amount of undercooling decreases, it is going to go larger over here. So if my undercooling decreases, so this is for delta T small, actually my undercooling decreases, this is where my delta T is very large. So it shifts left or right, and again, that's in our Wolfram mathematica demonstration that we published with our student previously. What happens if I have another system where particle nucleation cannot occur on any substrate, i.e. I'm nucleating a sphere, if I'm nucleating a sphere, I have to create an entire surface, draw this. So I'm nucleating on a substrate, so this purple curve, if it's the exact same system, it's going to look exactly the same, and I'm going to have the exact same critical radius, but my energy is decreased. So draw the curve of crystallization rate versus temperature. So I versus temperature for a homogeneous and heterogeneous solution. Label each curve. Explain and describe nucleation growth dynamics. So nucleation dominates at a low temperature, i.e. a high undercooling. My growth dominates at a temperature that's very, very high, or amount of undercooling that's very, very, very low. So if I'm homogeneously nucleating, it's going to take me a while. I'm going to have low temperatures in order to kind of start. And actually, my system, if this is my, for example, let's say this is Tm, it's going to take me a while to even start, and then I'm going to hit my peak further down the line. If I'm heterogeneously nucleating, for example, I don't need all this extra energy. The only thing that's stopping my system from basically nucleating particle is creating surface area. So if I have to create less surface area, I could start earlier, and I'll hit my peak earlier. So this would be hetero, this would be homogeneous. That's it. Little quick problem set, important, impactful problem set. We've done lots of these in-class exercises, so one of your problems in your exam will be on this problem set. So again, good luck, and I will see you all next time. That was a quick one. Thanks. Have a good one. Bye.